I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this ellipse area using double integrals. I've presented this topic before, but at a request of a particular viewer, I am representing it. In this video, the only difference being we are not skipping, or I am not skipping any steps. Anything with regards to the application of trigonometric identities, algebra, substitution, trigonometric substitution, the integration techniques, all of that, nothing is being taken for granted. Therefore, no steps are being skipped, and I won't breeze through it. I'll show you each and every step as it comes along for the viewer and or students who need to see every single step, and there's nothing wrong with that. What is it that you are looking at with regards to an integral? Are we doing the double integral such that we're doing an integral dx with respect to dy, or are we doing an integral dy then with respect to dx? When you are looking here, you decide, or I decide, I'm doing a horizontally oriented ellipse. And because I'm doing a horizontally oriented ellipse, it's sensible for me to do in this way. It's only because of the nature of the polygon that I'm looking at. When I'm doing a vertically oriented ellipse, it would be perhaps more suitable for me to do this. Why would that be the case? When you look at a horizontally oriented ellipse, you're doing an initial dx representation, and you can do here, the vertices minus a, and then the minor axis endpoints b and minus b. You can do minus a and easily move it upwards with respect to a dy, and then you can have your limits. I'm not putting minus b because I'll show you it'll be 0 to b, and I'll show you why that's the case. But that falls very well with a horizontally oriented ellipse, hence we do that. When you're doing this type of ellipse where your vertices are vertically oriented, your minor axis endpoints are horizontally oriented, then it's more sensible to do this. Think about it. You're doing something with regards to an inner dy integral having limits which are along a vertical dimension, but then you are integrating it with respect to dx in a horizontal manner. Hence, then you end up seeing from 0 up to b that dx integral comes into play. But what am I showing you here in this video? This one right here at the very top, and by means of this representation. But this could easily be adapted to a vertically oriented ellipse, for which then you would do integral dy and then dx. Here we're doing integral dx and then dy. And that's the nuance or the complexity that you have to keep in mind. Let's erase that which we do not need to see anymore. So we've decided we're doing it in this way, and we have a horizontally oriented ellipse, x squared over a squared plus y squared over b squared equals 1. We need to have a form of an equation which must be in the form x equals, not y equals. Why is that the case? Because while we are starting with an integral dx, for which you would do an equation in the form y equals format, in a form of a function, because the eventual integral is with respect to dy, we must convert it into an x equals format, because that's exactly the outer integral dictating what should happen with regards to the entire integral procedure. The outer integral is dy, therefore everything must be adapted to a dy integral, and the equations are then presented in the form x equals format, and we have to do that with exactly what we see here. Look, cross multiply and create common denominator. You'll have x squared b squared plus y squared a squared over a squared b squared. You have done a common denominator. A squared goes in here, b squared times it multiply here, b squared goes here, a squared times it multiply here, and you would have exactly what you see. Then you would cross multiply this. You'd have x squared b squared plus y squared a squared is equal to a squared b squared. Remember, here I'm trying not to skip steps, so for the students who need to see everything, they have it available. You are again solving for x equals format. You have x squared b squared is equal to a squared b squared minus y squared a squared, and then x squared is equal to a squared b squared minus y squared a squared over b squared. When you're looking here at this top equation, you can isolate a squared, or the top, you can say polynomial, a squared, you have b squared minus y squared, and then you have obviously b squared on the bottom. All of this is equal to x squared. When you solve for x, you're pushing the square on the other side, becomes a square root. You end up seeing a squared over b squared, and then you have b squared minus y squared. This a squared over b squared is a perfect square and a perfect root. You can push it out as a over b, and then you have b squared minus y squared. All of this is equal to x, and now this is what I needed, because eventually I'm integrating with respect to dy. Now let's create our double integral. We have the basic format right here, but we need the limits. When we're looking at the inner dx integral, I have with limits along the x-axis minus a and a, then I have an outer dy integral with respect to limits along the vertical, and I'm going to be modifying these limits. This is just rough representation only. The first modification is this. When I'm looking at this, I want to look at everything in the form of a function, so things will succeed the vertical line test. I'm eliminating this part on the bottom. Because I've eliminated, now I'm looking at a limit which is from 0 up to b, and you see this outer dy integral with the lower limit minus b, I've replaced it with a 0. But because I've done this and I'm doing an area representation, I'm only ending up calculating the area of this top part. The lower part has been skipped. Therefore, I must multiply everything by 2 to capture this lower half. And I can bring that right here, and or I can bring it right here. This 2 captures the part I've eliminated by means of employing everything with regards to functions that easily pass vertical line test. Now the other thing I must replace are these limits here. Our eventual integral is with respect to dy, and we have a double integral. The limits must demonstrate the effect of tracking along this function's curve, and you can only show that by means of bringing in a equation in terms of a limit. I had a minus a, so then I'm looking here at a minus a over b root b square minus y square. I had a positive a, so I'm looking at a over b square root b square minus y square. These represent my limits with respect to dx, which will eventually integrate with respect to dy 0 to b. This here is my double integral, and it's good. We just have to integrate this, but again we cannot skip steps. We integrate the dx, the inner integral, and we can look at the inner integral dx. You're looking at something like which was minus a and dx. When you integrate it, you have an antiderivative and you have a and minus a. I'm just using this as a shortcut to what you see right here. When you do this, you're doing here a minus a, you're doubling it, you're getting a 2a. So exactly what you see over here must be doubled. And what would that be? It would be a over b square root b square minus y square, and you double it. The same thing minus that same thing doubles it, and you have this. This is the outcome of your dx integral, which will now push outside your dy integral, and it'll come right here. I have a 2 which is already sitting outside, and it's going to hit with these items which are coefficients. 2 times this 2, a over b, is a 4 a over b. The end result of this dx integral is what remains, the item which you see right there in the square root, which is the b square minus y square, because I've already integrated this for you. It was easy. Now what remains is the square root b square minus y square and dy. So my dx integral has served its purpose, and we're looking at only now the dy integral. Again, everything you're seeing over here can very easily and perhaps more efficiently be done using a single integral. This is only a double integral application for ellipse area. How do you integrate this? You have to recognize you have a trigonometric substitution coming into play, because you're looking at something of the form a square minus x squared type of trigonometric integral, a constant square minus a variable square, except here your constant is a b, your variable is a y, but still a constant and still a variable. When you're looking at something like this, then you're thinking of certain types of substitutions for that trigonometric substitution procedure that's coming into play. You have a certain a prime value, which is what you would do for something like this. Here, don't confuse this a for this a, your vertex. This right here is a representation of a trigonometric substitution form, and I'm just modifying it by means of a prime. I have an a prime over here, which is representing the square root of b square, which would be a b. I have a certain substitution which will come in terms of my variable. Y will be equal to b sine theta, and then dy, the derivative of that, would be equal to b cosine theta d theta. These are the set of procedures which come into play when you're looking at a trigonometric integral of this form, and I have this form, a constant square minus a variable square and something, even if it's impacted by a square or some sort of power or a root, but it's still of this form, and we're doing it. Then I have to modify my limits theta 1 and theta 2 by means of everything you see right here and the limits you see right here. You put the lower limit in place of y. I have a 0 is equal to b sine theta. You have sine theta is equal to 0 or b, which is 0. Theta is equal to inverse sine of 0, which is equal to a 0. So I know my first limit is a 0. Now you look at the upper limit, bring it in place of y. I have b is equal to b sine theta. Take this on the other side. B over b is equal to sine theta. And then I know theta is equal to arc sine of 1. Put it on your calculator, you get a pi over 2, and you have pi over 2. So everything is coming into play. Our double integral, which has now become a single integral, which is now going through a trigonometric substitution procedure, has to be addressed. And I'm bringing it right here. I have a 4a over b anyways from the previous steps. I now have here a 0 and a pi over 2, and now I have to bring in these substitutions. So now what we will do, this part right here, we're going to work on this right here, then we'll bring the final outcome for you right here. It won't be messy that way. I have here a square root of a b square minus y square. I know b square represents my constant and my variable y is represented by b sine theta, and I'm bringing that right here and I'm squaring it. Then I have a dy which is represented by b cosine theta d theta, which is multiplying with everything as you see right here. When you look right here at the square root, you're looking at a b square minus b square sine square theta times a b cosine theta d theta. When you look again in the root, you can isolate a b square and you're looking at a 1 minus sine square theta. Forget this part for the time being, focus only here. Think about this trigonometric identity. Sine square theta plus cosine square theta is equal to 1. Cosine square theta is equal to 1 minus sine square theta. This 1 minus sine square theta is being shown for you right here. It can be substituted for a cosine square theta. So let's bring the cosine square theta right here. I have in the square root b square cosine square theta multiplying by b cosine theta d theta. You know these are perfect squares in a perfect square root. The b square will come out as a b, the cosine theta will come out as a cosine theta, and everything in the radical will be exhausted because it's coming out as a b cosine theta, which multiplies with b cosine theta, and you end up seeing from here a b square cosine square theta d theta, which has to be brought for you right here. You see the b square cosine square theta, the b square can be brought right out here as a constant. It's a constant, b square times 4a over b. I have the variable cosine square theta d theta. This right here is now the good end result of our double integral, which just is easy to approach. It's all now algebra and trigonometry from here. These coefficients can be easily simplified. I have a b square 4a over b. This b will cancel out with that. I have a 4ab. Then I'm looking at a 0 pi over 2. I have within here a cosine square theta. There's a power reducing identity. Cosine square theta is equal to, it's also called the half angle formula, but better known as power reducing identity. It's 1 plus cosine 2 theta over 2. You're eliminating a power and bringing in a variable which has here an exponent of 1. It's reducing the power, hence a power reducing identity. 1 plus cosine 2 theta over 2 d theta. Now the remainder of our procedure is involved with that, and you don't need to see any of this anymore. We've done our times 2 from the very beginning, and everything has played along. This times 2, which was sitting outside, became converted into 4ab by means of the procedures you saw. Now what we have to do is integrate what we see. What you're going to do is bring this denominator. You have 1 over 2, you're going to move it right over here, 4ab over 2. So the next step is this simplifying. You have a 2ab. You're splitting everything across this positive sign. You have a 2ab integral 0 pi over 2 1 d theta, which is meaningless to write a 1. You can just write d theta plus the same thing 2ab, because you're distributing this across two separate integrals over this positive sign. 2ab integral 0 pi over 2 cosine 2 theta d theta. You'll come to realize anytime you see something like this with 0 and a pi over 2, it will always zero out, but I'm not taking that shortcut here. I will show you exactly why it zeroes out. We're focusing now only on this part because our end result will only come from right over here. This is zeroing out. You focus right here. You can do a substitution. Let's say u is equal to 2 theta, du is equal to 2 d theta, and d theta is equal to du over 2. You can do u1 and u2 with regards to right here and your limits. 0 times 2 in terms of theta coming over there, it's a 0. Pi over 2 times 2, because this is your theta value, it's a pi. So what do you have? 2ab. Then you have 0 and a pi. You have a cosine u, and then you have a du over 2. You see this over 2? This over 2 cancels out with this. I'm looking here only at ab, 0 pi cosine u du. What's the antiderivative of cosine u? It's a sine u. The AB is meaningless because it's going to have no effect against a pi and a 0 with regards to a sine. Sine of pi is a 0 minus sine of 0 is a 0, and you have a AB sitting outside. All of the zeros out. Hence, this entirely zeros out, and that's a shortcut you should remember. Anytime you're looking at a cosine with a 2 theta, 0 and a pi over 2, the sine coming in, the limits, no matter what you have sitting out here, it'll always zero out. Your end result will always be from this half of the integral. Focus right over here. We have a integral d theta. The antiderivative is theta, and I'm looking at a pi over 2 and a 0 with a 2ab. You're doing the upper limit, the lower limit, and the difference of the two. You have 2ab times pi over 2 minus 0. you have a 2ab times pi over 2. The denominator 2, numerator 2 cancel out, you end up seeing a pi ab. And that represents the area of an ellipse, but of the whole ellipse, because this times 2 already took care of everything from the very start. And our procedure comes to an end. Thank you for watching. Have a good day.